All right, thanks. Yeah, thanks for the introduction, Isaac, and thanks for having me here participating at QHack. So my name is Jin-Sung Kim. I'm from the quantum computing team at Nvidia. Been at Nvidia for about 2 years now, so I manage our partnerships and our alliances and all of our technical collaborations. Like Isaac mentioned, I used to be a research scientist at IBM Quantum for several years. Some of you may actually know me from my time there when I hosted Coding with Qiskit for a season. I did my PhD prior to that at Princeton, studying electron spins in silicon systems for their use as potential qubits. So I've been in the quantum computing game for a long time. So I'll be talking to you today about our platform, what kinds of things that we're doing to support quantum computing at NVIDIA, and how we see quantum fitting in with kind of the broader HPC and accelerated computing ecosystem. So just to take a little bit of a step back and talk a little bit about NVIDIA's history and who we are as a company. We, of course, invented and built the GPU systems that enable essentially all of modern AI, including ChatGPT. In addition to this, NVIDIA has a really long and storied history in supporting scientific computing, starting from the advent of CUDA. And if you're not familiar with what CUDA is the framework that we developed that enabled developers to start using GPUs as general purpose compute machines. And it's really the technology that brings things to life like ChatGPT. So what CUDA enabled developers to do, back in 2006 up to 2012, start to use GPUs as accelerated computing machines. So this really enabled the advent of things like deep learning, generative AI. The photo here is actually a picture of Jensen Huang, our CEO, hand-delivering the first DGX A100 systems to OpenAI. I believe Sam Altman is somewhere in that picture as well. And what we see in quantum computing is a lot of parallels to what generative AI and machine learning were, 10, 15 years ago. So NVIDIA has a long history of supporting scientific endeavors like this and trying to support developers and giving them the best tools possible to do accelerated computing and scientific computing in the most performant way possible. So what are we doing at NVIDIA? The number one question that we get for the quantum computing team is, are we building a quantum processor? And the answer is no. But we are building essentially all of the tooling and infrastructure around building a useful quantum computer of the future. So essentially all of quantum computing of the future, useful quantum computing will be some sort of hybrid workload. So quantum computers are very, very specialized, and we believe will be very good at solving certain classes of problems in the future. But alongside each one of these problems are very difficult HPC problems that will require a lot of accelerated computing and really requires a heterogeneous and hybrid method of actually programming useful quantum workflows. So what does this mean in practice? So what we've done is built a platform to enable what we call quantum accelerated supercomputing. So at the heart of this is our platform called CUDA Quantum. So this is our platform and programming model for programming hybrid quantum classical workloads. It enables you to build really fast, very performant and flexible workloads leveraging CPUs, GPUs, quantum processors, and physical quantum processors together. We also have a collection of libraries for doing accelerated simulation. So this is called QQuantum. This kind of sits on the back end and helps you accelerate quantum circuit simulations on GPU systems. We're seeing speedups of a couple of orders of magnitude faster. So if your simulations are taking a couple of hours, they'll run in a couple of seconds on a GPU system. So really, really fast performance. This really enables the community to run very fast algorithms and do fast iterations for application development. And finally, we have on the system side a method of tightly coupling GPU systems to actual quantum processors. So what we've done here is partnered with Quantum Machines, who provides quantum control hardware for various modalities of qubits. And we built a system called DGX Quantum. And this provides a very, very low latency link between a GPU system and the quantum control system for various qubit modalities. So what this enables is for folks to start to actually look at what real-time compute alongside a quantum processor looks like. So why is this important? For a lot of things like optimal control, calibration, error correction, decoding. A lot of these things require a pretty heavy-duty compute alongside an actual quantum processor. So having now a low-latency link between these two things actually starts to enable users and developers to develop the error correction decoding schemes and things like optimal control schemes alongside the actual quantum hardware in real time. So a big part of our platform is to partner broadly across the entire quantum ecosystem. So we have a huge ecosystem of partners. We like to work with essentially everyone within the quantum computing ecosystem. So essentially every variety of quantum hardware builder, every qubit modality. We've accelerated essentially every quantum simulation framework. And we partner across a lot of application and algorithms developers as well, along with a lot of different quantum startups, as well as national labs and industry partners. So let me just take a beat here and talk about some of the success stories from our platform. So the first thing I want to highlight is our GPT quantum eigensolver work. This was done in collaboration with the University of Toronto and St. Jude Children's Research Hospital. This was work done with CUDA Quantum. So I think earlier in the day, the first author of this work, Koei Nakaji, gave a really, really nice talk about this work. But essentially, what we did was develop a novel generative pre-trained transformer, or GPT method, for computing the ground state energy of molecules of interest. So this is a really, really awesome workload that lies at the intersection of generative AI and uses it towards quantum computing. So there's a lot of workloads that invoke quantum machine learning. This is kind of the inverse of that, where we use machine learning methods to actually enhance the output of a potential quantum processor. So this is the first demonstration of a GPT-generated quantum circuit in the literature, and it's a really powerful example of leveraging AI to accelerate quantum computing today. So kind of the way that you can think of it is we have a pool of operators that analogously can be treated as words in a large language model. And we train this model to actually generate sequences of these operators from this operator pool to give us quantum circuits that have desirable properties. So this is a pretty generalizable method. We can train it to do to give us circuits with various desirable properties. In this first instance, we focus on the problem of quantum chemistry. So we're finding very good ansatses for quantum chemistry problems. This was executed using CUDA Quantum. As I mentioned before, CUDA Quantum enables you to do hybrid quantum classical workloads very performantly, very flexibly. The platform was designed for workloads exactly like this to combine Gen AI and quantum computing in one workload. We ran this on a very powerful GPU system called Perlmutter, which is a supercomputer hosted at Lawrence Berkeley National Labs in their NERSC facility. And we think this really opens the door to a wide variety of novel generative quantum algorithms for things like drug discovery, material science, and environmental challenges. So really starting to crack the door open for using generative AI methods towards quantum computing. So the next success story I want to talk about is work that we did with BASF. So they are, of course, a large chemicals company. And what we did was actually simulate a chelating agent, which is essentially a molecule that binds to metal ions. So this is very important for things like detecting toxic concentrations of waste metals within your water supply, or also detecting concentrations of toxic materials within the human body. So what we were able to do is use an approximate tensor network method using matrix product states and simulate a 60-qubit simulation of a molecule called FeNTA. This was a hybrid algorithm using CUDA Quantum. We ran this on our internal EOS H100 supercomputer. Some of this work was also done on Perlmutter at NERSC. But what this let us do is to start to probe kind of a scientific regime that is really difficult to probe with conventional simulation or techniques or with quantum processors today. This is a pretty difficult problem to simulate. So what we're able to do is get convergent results for the 60-qubit MPS method, and it's one of the largest simulations of its kind. So really starting to push the envelope of what's possible through simulation and to understand some really interesting novel techniques. This third use case that I want to talk about is work that we do with HPE Labs. So what we're doing here is actually simulating a 2D dynamic quantum phase transition. So this is a pretty heavy-duty condensed matter physics problem where we're simulating a highly entangled transverse Ising model Hamiltonian. So this is a full state vector simulation, meaning we're simulating essentially all of the information within the quantum system, and we're evolving that in time. And it's a very, very entangled system. So this is a 40-qubit simulation where it's a noiseless simulation, so we have perfect information of what's happening to the dynamics of each particle within the system. And what we're able to do is find where this dynamic phase transition actually happens in time. So this is really important for the design of new materials in the future. Applications within the space include designing things like new quantum sensors. So if you park a material near its phase transition, this gives you a very, very sensitive quantum sensor. This is a very difficult problem to simulate. So what we found is we've gotten about a 600x speed up using CUDA Quantum and A100 GPUs. This is done on Perlmutter as well. And compared to a CPU simulation, we estimate that this would have taken about 7 years to run on a CPU, but ran in less than an hour on Perlmutter. So really, really fantastic results. Really start to understand where these kind of dynamic phase transitions start to happen. And really leveraging the GPU infrastructure to get really good results that run under an hour. This final example that I want to show is work done by JP Chase and Argonne National Labs. So they've developed a very, very fast simulator for simulating the quantum approximate optimization algorithm. So this algorithm is very useful for kind of heuristic optimization methods, for example, for things like portfolio optimization, other financial optimizations, things within that flavor. And what they were able to do is integrate QQuantum, which is our SDK for accelerating quantum circuit simulation, and run this problem at supercomputing scale, do some scaling studies, and actually find that there is a numerical advantage to using QAOA for these specific types of financial applications. So this is really important because these are difficult simulations to run. You have to scale out the size of your simulation incrementally to kind of understand how the problem scales as you increase the problem size. And they're actually able to find a numerical advantage, which is really, really awesome. Okay, so let me switch gears now and talk a little bit just about our platform. Please stay tuned tomorrow for Efrat Shabtai's talk on getting started with CUDA Quantum. But I just want to give kind of a high-level overview of some of the tools that you'll have available to use for QHack. So CUDA Quantum is, of course, our platform for hybrid quantum classical algorithms and application development. It's a single-source C++ and Pythonic programming model. It includes a high-performance compiler for hybrid CPU, GPU, and quantum processor systems. It's quantum processor agnostic. We have a lot of quantum hardware partners today that have integrated CUDA Quantum into their software stack already, and we're working with many more to integrate into their systems. And it's interoperable with leading scientific computing and AI tools. So like I said before, this is the platform that we use for the GPT quantum eigensolver work and some of the other examples that I mentioned previously. Just to give you a quick flavor of the performance that you can get, it contains a very fast compiler. So for things like a single BQE iteration, this is a quantum chemistry problem. As you increase the number of qubits in the system, the synthesis time and the compilation time actually starts to matter. So there's a GPU to GPU comparison where we're comparing CUDA Quantum running a single iteration of this problem compared to another Pythonic framework, and we're getting a very substantial speed up from the compilation stack. I'll just mention that CUDA Quantum 0.6 is now available. It's recently available as of, I think, a couple of weeks ago, so definitely check out the new features. And I want to talk a little bit about QQuantum, which is our our SDK for accelerating these simulations using GPUs. So underneath the hood of CUDA-Quantum, cuQuantum is actually providing the acceleration libraries for running the quantum circuit simulations on GPU and providing these hefty speedups that we're seeing when we simulate these systems. So you can simulate ideal or noisy qubits with state vector tensor network methods. I referenced our tensor network library before in our BASF work. And it actually supports GPU supercomputing with multi-node and multi-GPU circuit simulation functionality. So as an end user, if you want to scale out the size of the problem that you're addressing, you don't really need to worry about that. We provide the APIs and all the functionality for that to happen underneath the hood. So it makes it very simple to run these simulations at scale. And just to give you a quick flavor of the speed and the performance of cuQuantum, I'm showing a couple of different quantum algorithms here and running them on different numbers of GPUs. As we increase the number of GPUs used for these simulations, you see a pretty substantial speed up in performance of the simulation. So the fastest one here is Shor's algorithm, running on 8 H100 GPUs. And we're seeing about almost a 400x increase in performance compared to a pretty hefty CPU system. So just really fast performance here. It really will increase the throughput of your research and iterations of any sort of algorithm or application development. The last slide I want to show here is results from our tensor network library, cuTensorNet. So what we were able to do a couple of years ago is just simulate a massive system for solving a max cut problem. We were able to simulate 5,000 qubits on 20 nodes of a DGX A100 system and get very good accuracy results. So tensor network methods are fantastic for looking at systems at scale, depending on the application, depending on the depth of the circuit. But it's a really, really useful complementary tool to simulate large quantum systems, depending on the application. Okay, I think that basically brings me to time. So I want to thank you for your time. Hope that was useful for giving you a flavor of what our platform has helped enable. And I definitely want to encourage you to tune into Efrat Shabtai's talk tomorrow. She's our PM for CUDA-Quantum. And she'll have a really, really nice demonstration of how to get started with CUDA-Quantum for your own applications and for your own projects in QHack.
All right. Thanks so much, Jin-Sung. That was really interesting, actually. Thanks so much. We have a lot of questions, so I'm going to try and zoom through as many as I can. But if your question doesn't get answered here, guys, go to the Discord. Jin-Sung will be there, and any questions that didn't get answered, you can ask there. All right. So we have a question from Mega Make on Twitch. Does the platform provide a common quantum programming language like CUDA shader languages, or support standard open source QPL like Qiskit?
Yeah, so the programming environment is very similar to essentially all the other ones that you're probably already familiar with. So you basically allocate qubits, you apply gates, you do readout, you ask to sample the circuit. There's also higher level libraries, but if you're familiar with things like Qiskit or Cirq or PennyLane, the programming environment looks very similar to that.
Cool.
Kind of underneath the hood, so CUDA-Quantum is open source. We also compile down to an intermediate representation called the QIR, which is how we actually interact with our quantum hardware partners. Cool.
Okay. Hopefully that answers your question, Mega Make. Just a comment from Entiato. Thanks, man. Awesome presentation. Another question from Dentucky Kirby. Quite a bit of compilation flavored talks this QHack. Is this what you think companies are trying to shift towards programming-wise? Like, should I learn LLVM instead of being a Python ninja? Lol.
So you can if you want. It's important. It's an important problem. If you want to just program in Python, you can do that with CUDA-Quantum, and it'll just compile down to LLVM. And as a user, you don't really need to worry about that. But if that's something that you're interested in, it's open source, so you can also start to tinker around with the compiler stack within CUDA-Quantum.
Cool. All right. There's a lot more questions we didn't get to. So yeah, definitely go on the Discord, guys, and ask them there. Thanks so much again, Jin-Sung, for your time and your presentation. Really appreciate it. And for everybody here, definitely check out Ifret's talk tomorrow for getting started with CUDA Quantum. That's on Friday at 1 p.m. Eastern time. Thanks again, Jin-Sung, and chat soon. Cheers.
All right. Thanks a lot.